And greetings from Indian Institute of Remote Sensing. So as part of the EduSat courses, today we will be talking about geospatial technology for disaster management studies. And I will be dealing with mostly the challenges and opportunities in this particular area. So when we talk about the exposure, it is the component of the society which is affected. There is a people or property. And vulnerability is basically the ability or the inability of the society to resist the threat, which depends on the economy, the environment, or the adaptive capacity of the society. And a subset of all these three is the risk. So when we talk about natural hazard or natural disaster, it is all these components which we talk about in our lecture. So disaster risk management framework was first formalized as part of the Hugo Framework of Action in 2005, which was adopted for the next 10 years, which basically dependent on the which basically dependent on the governance and the cooperation in one hand, and the risk identification, risk reduction, and risk transfer on the other hand. So when we talk about the risk identification, it's the historical hazard data analysis, the changing hazard trends, and expose assets or vulnerability, which basically constitute the risk identification. Risk reduction involved the preparedness, early warning system, emergency planning, response planning, and increasing their capacities, and also the mitigation and prevention. And the risk transfer was through various mechanisms like insurance, bonds, or other alternative risk transfer mechanism. And to realize this, it was basically through the information sharing and capacity building. So why is this coming? So when we come out from 2005 to 2015, so during 2015 we had another conference to take up the disaster management and disaster risk reduction further. And in 2015 we had the Sendai framework, which basically aims to achieve a substantial reduction of disaster risk and losses in lives, livelihoods, and health in the various sectors like economic, physical, social, cultural, environmental, and business communities of countries over the next 15 years. So it had 7 targets. That is to reduce the mortality, reduce the number of people affected, reduce the economic loss, and reduce the damage to critical infrastructure and services through improvement in disaster risk reduction, improvement in international cooperation, and improvement in the early warning and risk information. To achieve these 7 targets, 4 priorities of action were identified, which are the understanding the disaster risk, which translates into the physical basis of the disaster or the science behind the disaster. Then investing in disaster risk reduction for resilience, both for infrastructure, in space-based as well as ground-based. Then strengthening disaster risk governance to manage disaster risk. So when we talk about governance, it's basically availability of proper information and timely information. So it's dissemination of the information. And we have the 4th priority of action, which is enhancing disaster preparedness for effective response and in recovery, rehabilitation, and reconstruction, which translates something into like development of early warning system and the logistics. So the sustainable development goals, which was also formulated in 2015, basically takes a lot of inputs from the Sendai framework. And how they are related, I'll just show you in this slide, which identifies the aspects like number of deaths or reduction in number of deaths, direct economic loss, direct disaster and economic loss in relation to disaster damage to critical infrastructure, number of countries who have good national and local level DRR strategies, and how the local government are adopting and implementing the disaster risk reduction strategies at local level, which is in line with Sendai framework and sustainable development goals. So you see the goal number 1, that is no poverty, goal number 11, sustainable cities and communities, goal number 13, there's a climate action. All of them have the Sendai framework integrated into it. So when we talk about the disaster management program of ISRO, because the entire geospatial technology for disaster risk reduction got its impetus, or what was basically originated as part of the disaster management support program of ISRO. So this is an institutional mechanism which we have a disaster management decision support center at National Remote Sensing Center at Hyderabad. And this has nodal agencies in various stakeholders like Ministry of Home Affairs, Prime Minister's Office, Ministry of External Affairs, Cabinet Secretariat, NDMA, NIDM, agencies, NGOs, etc. And we have almost 5 areas where the space technology is providing a very critical inputs, like monitoring and damage assessment of the natural disasters, that is after the disaster. Then maintaining a national database for emergency management, for rescue rehabilitation and basically governance, emergency governance during disasters. Then we also provide space-based communication for emergency. Then strengthening the early warning systems and development of various sensor network which you already have. So some of the key developmental efforts which we have taken up is airborne SAR, the development of communication equipments. We are also providing support to the IoTs and developing constellation of Earth observation satellites. There are some key areas where critical R&D inputs are being carried out, like landslide, earthquake precursor studies, extreme weather events, forest fire risk management, etc. And we are also taking care of our international commitments on the International Charter on Space in Major Disaster as part of UN Spider and Sentinel Asia. So when we talk about the space technology in disaster management, first is identification of disaster, where the observation from space plays a very important role. So in event of disaster, identifying the area, the extent, and the location of the disaster through observation. And once we identify the extent, magnitude, and location of the disaster, using satellite-based location services, identify the best possible routes to provide the relief and rescue. And also use the space-based satellite communication system for basically communicating to the global community about the extent of the relief and rescue which are required in that area, and what are the types of rescue relief material which are required. In fact, if you take into account, space technology, in fact, is very critical in all the aspects of the disaster cycle. So after we provide the initial succor, that is relief, then comes the rehabilitation of the people who are affected, reconstruction of the damaged infrastructure in a way which is more robust and resilient to the upcoming disasters. Then mitigation and preparedness through development of early warning systems, where space technology again plays a very important role. So when we talk about the space-based observation, we have the entire gamut of observation, right from a very high temporal resolution every 15 minutes to a very detailed resolution of some 20 to 40 centimeters, where you can detect the various damages to the infrastructure. But above all, remote sensing provides us the ability to observe in 3D. So the 3D imaging capability of remote sensing provides us the digital elevation model, which helps us to identify, especially for the flood and other type of disasters, the areas which are likely to be affected or inundated because of the impending or coming disaster. So when we talk about the natural disasters in India, India is actually vulnerable to a wide range of natural hazards like flooding, cyclone, drought, extreme heat waves, landslides, wildfires, earthquake. You name any disaster, say except say a volcano or a volcano. In fact, we also have an active volcano, but since it is in a place where there is no habitation, so we do not consider it as a natural hazard. And recent studies have shown that as a result of climate change, the intensity, duration, and frequency of the weather-related disasters are likely to increase. So, when we talk about geospatial technology for monitoring disasters, what does it provide us? Satellite data provides us a temporal observation and the patterns on the surface of the Earth, which provide us the scientific understanding in form of various maps, like hydrological maps, geomorphological maps, lithological maps, structural maps, land use, land cover maps. There are in number of scientific translation of the temporal observation and patterns observed by the satellite data. And once you have all these information stacked one over the other, talking to each other, you can develop various models. And these models can help in understanding the processes as well as the forecasting the various disasters which are as a result of the Earth systems models. So we'll just go one by one the various disasters which are observed. So we start with a geological disaster, and one of the most spectacular geological disaster is earthquake. Here, remote sensing plays a very important role. I would say not just remote sensing, but space technology. So we have the observation and monitoring, wherein using advanced tools like interferometric SAR, we can detect the subsidence or the changes on the Earth's surface as a result of the earthquake. And this can be picked up very, very, very easily using the various advanced techniques. And the events like earthquake also leaves a few scars or their traces on the surface of the Earth, like folds. These also can be very well captured by a trained geologist using Earth observation data like Landsat TM or LIS3 to provide us the various geomorphic elements, which shows us the areas which are fragile. Apart from that, during earthquake, a thermal anomaly is also observed because of emission of hot gases or vapors from the Earth's crust. So those thermal anomalies can also be picked up very easily using the earthquake, using the thermal data from the various satellite sensors. This is what we have talked about, the observation and monitoring of the earthquake or a geological disaster, that is earthquake. But various space-based observation can also provide a level of forewarning and risk analysis. For example, the continuously operating reference stations, which are there across the world, which are nothing but a very high resolution GPS, which is fixed at a point and continuously providing the location of that area. Using this continuously operating reference stations, we are able to track the movement of various global plates, continental plates, and also to observe where the maximum amount of pressures are being built. So all these indicate that many of the plates are actually moving in different directions, such as you have the Indian plate, which is moving in a northeast direction. It's not just moving in a northeast direction, it's also sort of rotating in an anti-clockwise direction. So the strain which is there in the Himalayan region is actually not uniform across the Himalayan belt. There's another area which is basically which people are working on is the anomaly in the total electron content in the ionosphere. It has been observed that the total electron content, ionospheric total electron content, shows an anomaly just before an earthquake event, major earthquake event. And these have been tracked, are being tracked across the world. It is basically through the observed due to the attenuation in the signals which are being transmitted by the continuously operating reference station. Although this is still a evolving area and we don't have a very, what you would say, a strict or a very effective forewarning mechanism, but it is observed that something like 14 days to around a few hours before an earthquake or major earthquake, anomalies are almost at all time detected. But thing is that we are still not able to pinpoint the exact cause as well as the what do you call temporal occurrence of the event. So we cannot just tell people over an area of something like few thousand square kilometers that we may expect an earthquake and you can evacuate. So you cannot basically do it. So we need something more robust than this. Then another geological disaster is a landslide, and here also Earth observation helps a lot in monitoring the landslide events, because you have the scars which can be detected very easily, and using various models you can determine the hazard and vulnerability of a region for an earthquake. Oh, sorry, a landslide. Then we have the Rishiganga rockfall induced flash flood, which we had in Uttarakhand in 2021. This is a very classic example of how one event can lead to a cascading of events resulting in a major disaster. So in February 7th of 2021, a big chunk of rock, you see here, this is a big chunk of rock. I'll just give you an idea about how big it was. It is something like 3 football fields, 50-meter thick. So that big chunk of rock fell down from the Ronti Glacier and basically fell in the Rishiganga Valley. This is the Rishiganga glacier, and it fell in the valley around 2 kilometers down, and the impact was so much that the entire snow melt as well as the permafrost, which has accumulated over years, melted, and the entire slurry rushed down the valley and damaged everything downstream. So the amount of water which was generated or slurry which was generated was something like around 30 to 40 stories high. And it damaged the entire area. It also damaged the Tapovan hydropower site, which was downstream, and more than 250 people died in this particular area. So this is an example of how a landslide, I wouldn't say a landslide, but a rockfall resulted in a flash flood, which killed a lot of people. Then there are the hydrometeorological disasters like flood. We of course experience it every year in many parts of the country. So when there is a flood, normally it is during monsoon, and most of the flood in Indian subcontinent are because of precipitation induced flood. So when there is a precipitation or rainfall, you have the cloud covers. So normal optical imaging is not possible. However, we have the synthetic aperture based radar, which provides us microwave data. And this microwave data, because it has a larger wavelength, is able to penetrate through the clouds. And we can get a very accurate estimation of the area inundated because of the flood. And this input plays a very key role in providing the relief and rehabilitation, and also directing to the relief to the areas where they are most needed. But it's not just that. We also have a very effective early warning and risk system for floods, because this rainfall inputs, they can be predicted. At least we can have a short-term prediction provided by the various models like WRF models. And we also have the various rain gauge and radar, Doppler radars, which can also provide us an estimation about the rainfall which is expected in an area. So using this information, we can run the various hydrodynamic analysis using various hydrodynamic models to generate the real-time flow. And this pre-computed real-time flow can be basically modeled to identify the various inundations as a result of different levels of rainfall. And this can be saved as a library. And when there is a rainfall, the most appropriate pre-computed flood map can be picked up based on the rainfall and the modeled as well as the actual rainfall data, and the people from those areas can be evacuated. In fact, this is very much being used in the Assam, where people are using this model for the various flood early warning system in the Brahmaputra River basin. Then we also have the other types of hydrometeorological disasters like extreme weather events, flash floods. In 2013, we had a major flash flood event in Kedarnath, which resulted in deaths of few thousand people. So these are basically high frequency extreme rainfall events, generally at an elevation of over 3,000 meters. And because of the nature of the event, there is a very less amount of forewarning, and we basically experience a lot of loss in life and property. So I'll just give a brief description of what happened in the Kedarnath in 2013. So during June of 2013, there was an extreme rainfall event which triggered a number of landslides and caused widespread damage. So what happened was that over Chora-Galibari Glacier and Companion Glacier, there was an extreme rainfall event, and a lot of debris and snow, along with water, was washed into the Chorabari Lake, which was just next to the Chorabari Glacier. So once the lake got filled, the moraine dam, which basically blocked or had the lake, which was because of the moraine dam, that lake was there, it got breached, and the entire water flowed directly onto the Kedarnath town, which is situated just below it. You can see from the video, this is the first helicopter sortie after the event. So this was the Chorabari Glacier Lake, and the breach happened here, and the entire water flew down, flowed from here into the valley, which had the Kedarnath town. So this was the extent of devastation we had. And using high resolution Cartosat data, we could identify the areas or the buildings which were totally damaged, totally washed off, some buildings which were partially damaged, and the buildings which were not damaged. But it was not all. In fact, remote sensing helped us to even identify the potential of rescue and rehabilitation using a digital elevation fly-through, which was created even before the aircraft could fly there. So this is a digital elevation draped with a high resolution, I would say Cartosat and list 4 merged data. And we could very well identify the areas which were damaged and the extent of damage to the roads and other pathways which were there. So you can see the Chorabari Glacier or Chorabari Lake, there's the Chorabari Tal, and on the north of Chorabari Tal is the Chorabari Glacier. Then we have the hydrometeorological disaster or the drought. In fact, this is one of the disasters which is not that much spectacular, but it creates a lot of impact on the economy of a country. And monitoring drought as well as having an effective early warning droughts system is paramount to basically protect yourself from the shocks which can be caused because of this particular disaster event. So when we talk about drought, there are 3 types of drought. There is a meteorological drought, which is basically a departure from the long-term average rainfall. Agricultural drought, which is because of inadequate moisture and rainfall, and hydrological drought, which is the water shortage due to an imbalance between the surface water and the groundwater. So using a number of data sets, both space-based as well as ground-based, and also ancillary databases from the various surveys, an effective drought early warning system has been developed, which can predict the time of occurrence, the spatial extent, duration, and severity of the drought, so that the areas which are vulnerable to drought can be identified and appropriate cropping practice can be suggested to the farmers. And also having an early warning system can have a big impact on maintaining the price trend of food and feed. Then we have the coastal disasters like tsunami. Tsunami is basically an underwater earthquake which causes a ripple on the surface of the earth. And when it moves to the coast, it causes huge waves, which leads to a lot of devastation. So using satellite-based observation, we can identify and monitor the destructions caused due to the tsunami. But more than that, space technology helps a lot in developing an early warning and risks analysis system. So we have a tsunami early warning system at IIRS, which basically consists of a number of pressure sensors, which are installed at the bottom of Bay of Bengal. And all these pressure sensors are mostly these pressure sensors are along the various faults and the ridges. So these pressure sensors are linked to the GPS buoys, which have satellite-based communication to the simulation and modeling center that is in IIRS. So in event of an earthquake, these sensors pick up the signal and relays it to GPS buoys. And within a fraction of a second, this information is sent to the tsunami early warning system at INCOIS. Now, this tsunami early warning system as INCOIS has run a simulation of more than 90,000 scenarios in the of earthquake, underwater earthquake in Bay of Bengal. And based on the what you call signal, they identify the most suitable scenario from the library, and using that as a base, they send the warning to the people of the effect of the potentially affected areas for taking them to safer places. In fact, this warning is sent through loudspeaker system. It's sent through mobile as well as through radio. Then we have the other form of coastal disasters like sea level rise, storm surges, incursion of salt water into aquifer, which actually affect a lot of human society as well as human health. Another of the coastal disasters are the cyclones. In fact, this is one area where space technology has played a huge impact in saving the lives. So now using our Earth observation system, we are able to monitor and track the movement of the cyclones and also identify the extent of damage and inundation because of the cyclone. In fact, I'll just give an example. Using INSAT 3D and 3DR, as well as OceanSat, the cyclone tracking and landfall has been very accurately modeled. Along with that, the wind speed and associated rainfall is also can be estimated, and the damage assessment as a result. So in 1999, we had a very big cyclone in Odisha. That is a Odisha super cyclone. I think many of you remember it. In this particular event, more than 10,000 people lost their lives. Now, we come back to 2013. We had Cyclone Falin. In fact, Cyclone Falin was more intense than the Odisha super cyclone. But in this event, the number of people who lost their lives was in single digit. And this was because of the effective early warning system and the preparedness of government of Odisha for this particular event. So after the Odisha super cyclone, government of Odisha has built cyclone shelters across the coastal region, and they have also built up an effective logistic system for upgrading the infrastructure and essential services in event of disasters. So you can see how effective early warning system with the help of space technology can really play an important role in saving lives. Then using geoinformatics, we can also provide a human health and disease surveillance. And then we come to the environmental disasters. Nowadays we basically hear about the heat waves. Very less work has been done on this. So using Earth observation data, we can have a good spatial modeling of the heat waves, which can help us in spatiotemporal variation, identifying the spatiotemporal variations and other hazardous region, and how the various land use land cover transformation is able to is basically producing the skewedness in the heat wave events. So using robust models and various indicators, we could identify the heat wave hazard region and overlaying it with the population, we can identify the heat wave risks. So you can see this is the heat wave risk map of India, which has been developed using various techniques, geospatial. Then we have another form of environmental disaster, that is a forest fire. Here also Earth observation plays a very important role in observation monitoring, like identification of active fires. It's a well-established procedure, as well as identifying the affected areas because of forest fire. There's the burnt areas. So we just don't stop at that. We also are working on forewarning and risk analysis, which uses a combination of weather-based parameters as well as the fuel parameters and the local parameters to identify the areas which are at risk for the next 24 hours. And once a fire has already occurred, how it is actually spreading. That also has been modeled using a combination of network, it's a complex network algorithm. Then we have the weather WRF, that is the weather forecasting models, and which includes the wind speed, wind direction, the precipitation, temperature profile, etc., etc. And also another algorithm, which is basically what you call cellular automata, which identifies how a particular cell or how the fire will move from one cell to other. So using a combination of these three models, we have been able to develop a very good forest fire spread model, and it is pretty accurate. It has an accuracy of more than 80%. Then again, space-based observation can help in the decision making. So this is a digital flight through of the Uttarakhand during a extensive fire episode in 2018. And you can see how the forest fires are spread across the region. In fact, you don't even need a helicopter survey. You can simply create a digital fly through and observe the damages across the state. Then we have the environmental disasters, another form, which is like the atmospheric pollution and dust storm. As you see, we have very poor air quality over Delhi, especially during October, November. It's partly due to the climatic conditions which are there as a result of the thermal inversion along with the changes in the wind direction and patterns, which is aggravated by the crop residue burning during this period in Punjab and Haryana, which aggravates the total suspended particulate matter and the black carbon over Delhi and the northern part of the country. And during this period, because of the thermal inversion and which restricts the dispersal of the pollutants, the entire area becomes very non-conducive for human habitation. Then using Earth observation, you can also detect some of the other industrial hazards and disasters, like identification of gas leaks in pipelines using drone-based observation, hyperspectral observation, identifying the various hazardous fire in waste dumps, identifying the oil spills because of the collision of ships and other industrial hazards. Then we also have the natural disasters which are because of the climate change, like sea level rise. In fact, it has been I would say people are speculating that because of the climate change, there may be a rise of something like 1 to 4 meters. And many of the island countries you observe are just 1 or 1.5 meters above sea level. So in event of a sea level rise, where will these people go? There will be a big humanitarian crisis across the world. And it's not just that. There can also be something like large-scale singular events. As you all know, there are warm currents and cold currents in the oceans. And it is these combination of warm and cold currents which maintain the climate as we know now. So this climate change is actually resulting in melting of the polar ice caps. And IPCC Assessment Report 5 has speculated that, I won't say speculated, but has identified with a high level of confidence that the Northern Hemisphere sea ice extent may disappear by 2100. So if this Northern Hemisphere sea ice extent, that is the ice over the Arctic Circle, disappears, this will result in the decrease in the thermohaline condition in the Northern Ocean. Now I'll just take an example of one of the ocean current. That is the one you see, which is from the Gulf of Mexico, goes to north of Europe. This is known as the Gulf Stream. And it is this Gulf Stream which basically keeps Europe ice free. You see, Europe and Greenland are more or less in the same latitude, northern part of Europe. Whereas Europe is ice free, Greenland is covered by ice throughout the year. So because of the decrease, what happens is that this warm current, which goes from Gulf of Mexico to the north of north of Europe, meets the cold water from Arctic Circle, and it becomes dense and it goes down like a waterfall. And the amount of water which actually goes down in this region in 1 hour is more than all the water in all the terrestrial ecosystem. That is, you combine all the waters of all the rivers and all the lakes on the terrestrial ecosystem. And in 1 hour, that much water actually goes down. And this is like a conveyor belt. Now, because of the changes in the thermohaline condition in the Northern Ocean, suppose this thing doesn't happen. This warm water doesn't cool down enough, doesn't become dense enough to go down. This conveyor belt might stop. And once this conveyor belt stops, Europe, half of Europe, I would say, will be covered by ice, which will lead to a huge, I would say, a huge issue in the food security across the world. I'll not go into much detail about satellite navigation, but I'll just emphasize on one aspect of satellite navigation, that is the Indian Satellite Navigation System, that is IRNSS, and how it has played a big role in emergency communication. In 2017, we had the cyclone Oki, in which 70 fishermen from Kerala lost their lives. Now, once a fisherman goes out into the sea, there's no way you can communicate with him, except perhaps you have a satellite phone. But most of the fishermen are not rich enough to afford a satellite phone. And when these fishermen goes out into the sea, they do not come back in the same day. They basically go out on the sea sometimes for more than 10 to 15 days. So when they went out in the sea, there was a cyclone which was forming in the south of Sri Lanka, which moved north towards the Arabian Sea. And there was no way these fishermen could be warned about the impending cyclone. So 70 fishermen lost their lives. Now the government of Kerala requested Indian Space Research Organization to at least do something so that those people can be informed about the impending disasters. So we had a channel in our IRNSS satellite system, which consists of 3 geostationary satellites and 4 elliptical orbit satellites. So one of the geostationary satellites could provide an SMS communication. So ISRO developed a small device which was Bluetooth enabled, which could be linked to the mobile phone of the fisherman. And these devices were fixed on the mast of the ship, were powered by the ship's engine, and this provided a two-way SMS system for communicating with the sailors. In fact, now the systems are so well developed that they can even identify when a fisherman is crossing the international maritime boundary when they are at sea. And we also have a very good communication network through VPN based system for disaster management support, because in event of any disaster, it is the communication system which are knocked out the first. So in that we have a VPN based disaster management communication system, which consists of a hub station at Ministry of Home Affairs at New Delhi, which is the primary node, and user nodes which are spread all over the country in every district. And they have the capability to provide voice, data, and video traffic between any 2 nodes. And using this communication system, in event of disasters, we are able to provide the telemedicine support to the ground people who are working in rescue and relief. There is another aspect which is the crowdsourcing, which actually helps in use of social network for prioritizing the rescue and relief, as well as identifying the damages to the disaster prone areas. Then we have the National Database for Emergency Management, which is a database which has a disaster dashboard, an incident reporting, data visualization, decision support tools, interaction portal, resource management, and there are a number of features of this NDEM. And the database which is there has almost all the databases, like road layer, the village layers, the hospitals, the location of police stations, the location of NDRF. You name any of the spatial data which is available, which it has to be there in the NDEM. And this database is used for providing effective disaster response through various decision support tools, like proximity tools or a network analysis tools or multi-layer analysis tools, and even the users can use the specific data tools for this. We are a part of Sentinel Asia, so presently we have around 110 members from 94 organizations from 28 countries of Asia Pacific region. And in event of a disaster, any of the member can request the emergency observation through any of the satellites of the member countries, and it's open to abstract member. And through international charter also, we can use the entire space asset of all the nations for effective disaster monitoring as well as response. Thank you very much. So I will have a 5 minutes break, and then we will again take some of the questions. Thank you.